In this section, we'll examine several different types of chemical reactions. The first type is a synthesis reaction. Here, two reactants will come together to form a single product. The general form of it is A plus B yields AB. Let's try it for a reaction between iron and oxygen gas forming iron 3 oxide. So from our past, we know that iron 3 is going to be the type of iron that donates 3 electrons. So we can start to write the chemical equation just by putting down the reactants on the left and then putting an arrow, which is a yield sign, pointing toward the product. And the product is Fe2O3. Now we can see that the number of iron atoms we have on the left does not match the number of iron atoms on the right. And the number of oxygen atoms on the left does not match the number of oxygens on the right either. So just like an equation in math, what you have on the left has to equal what you have on the right. And so we have to do what's called balancing the chemical equation to make the reactants equal to the products in number of atoms. So we'll typically put down blanks in front of each item here, and we'll try to put coefficients out front in order to make the equation balanced. We shouldn't try to change the subscripts of the items here. So for example, I should not change O2 to O3. Okay, and change the subscript of iron from a 1 to a 2. That's actually a common mistake in balancing equations. You don't want to do that. You want to just let the compounds be what they are and only change the coefficients out front, which are numbers that we multiply times the item that's involved. Alright, so one of the most logical things to do here would be to increase the number of iron atoms that we have on the left by putting a 2 out front. Iron's alone, so it's easy to change it in order to match what's on the right. We know we're going to have to at least have a 2 out front of the iron because before, without the 2, there's no way we could achieve balance. Next, we want to see if there's a way we can change the oxygen to match the number of oxygens on the right. If we want to restrict ourselves to integer coefficients, then we can't really do it. We could double the oxygen here, and then what we're supposed to do is multiply the coefficient times the subscript to figure out how many atoms that would really be. So this would be 2 iron atoms, and this will make 4 oxygen atoms. But even though the irons would be balanced with this configuration, unfortunately the oxygens would not. We would have 3 on the right and 4 on the left, so 2 can't be the right choice here. Instead, let's try a 3. If we make that into a 3, then that'll give us 3 times 2, which is 6 oxygens on the left. And if we go and put a 2 onto this one, onto the product, then we would multiply the 2 times the 2 here and a 2 times the 3 there. That'll change our number of irons and oxygens. We would now have 4 irons and 6 oxygens on the right. This is great because our oxygens match now. The only problem is our irons don't. So we're going to have to go back to the choice we had made for iron and change it. And let's make it 4 irons. Now we see that our irons match on the left and right, and our oxygens match 2. So this is going to be the correct chemical equation to write for iron combining with oxygen to make iron 3 oxide. Now it can also be useful in these situations to make a picture of what's happening. So iron is going to come together with O2 to make Fe2O3. So if we draw the situation, we could show how for our products iron is bonded to 3 oxygens. This is the iron 3 type, which means each iron is going to give off 3 electrons, and each oxygen wants to accept 2. So this would be a diagram of the result here, Fe2O3. And the idea with a chemical reaction is you can bring in more copies of the things involved. So this alone can't be the right solution because there's not enough iron on the left to match the amount of iron on the right. There's also not enough oxygens on the left to match the number of oxygens on the right. So we can see where this iron goes, and we can see where those 2 oxygens go. But we have 2 elements here on the right that we don't know where they came from. So this can't possibly be the right combination. What we can do is bring in more irons if needed. So bring in 1 more iron on the left. That would be like putting a 2 out front. Now we see that the iron is all accounted for. But when you bring in more oxygens, if I was to put a 2 out front of there, all I could do is bring in 2 more. But that's too many is the problem. See, if we were to have this guy go there, there's nowhere for the other oxygen to go, and you can't have that. You have to have equality on the left and right. So this shows that 2 is not the right choice to make here. What I'm going to do next is I'm going to add a 2 out front of the iron. I'm going to add a 2 out front of the Fe2O3. But as a picture, what that would mean is bringing in another copy of that entire product. So we'll have to bring in 2 more irons and 3 more oxygens. All right, now our oxygen here has somewhere to go. But we see that we still need 2 more oxygens. So we're going to get rid of the 2 out front here and put a 3 there and bring in another copy of the oxygen gas molecule. Now all our oxygens match up on the left and right. But we're going to have to bring in 2 more irons on the left and that's going to make us change our iron coefficient to a 4. So I hope that drawing helps explain how the chemical balancing is done. A lot of times we don't draw the picture because some of the pictures could get really large and it could be tedious and difficult to draw. But I just wanted to show that as an example of what we're doing when we're balancing the equation. The next type of equation we might see is a decomposition reaction. This is where a compound of AB may break down into its components A plus B. An example of this could be water breaking down through electrolysis into hydrogen gas and oxygen gas. Alright, so we'll start by putting our molecule of water here on the left, and it's going to break down into hydrogen gas and oxygen gas. Now those molecules just are what they are. You don't want to change the subscripts at all. Like I said before, you just want to come up with coefficients that would achieve balance in the situation. And a lot of times with these, you just want to look for what changes are absolutely required. I see that I've got 2 oxygens on the right, and I've only got 1 oxygen on the left. So if we're restricting ourselves to integer coefficients, it is absolutely necessary that we bring in another water molecule. This way we'll have 2 oxygens on the left and 2 oxygens on the right. But this also means that we've got 2 times 2 equals 4 hydrogens. So let's change our numbers now to reflect the coefficient being there. 4 hydrogens and 2 oxygens on the left, but only 2 hydrogens and 2 oxygens on the right. The next change that's absolutely required is we have to double the number of hydrogens on the right. Now we'll have 4 hydrogens on the right, and we'll just leave this as a 1, and then we have balance. In a single replacement reaction, there will be a switching of partners. Let's see, A plus BC will yield AC plus B. So whereas the C was with B originally, now C is with A. Let's try it with zinc reacting with hydrochloric acid HCl. What will happen is the chlorine here will switch partners. It won't be with the hydrogen anymore, it'll go with the zinc instead, because zinc is a metal and chlorine's a non-metal. So we'll form ZnCl, and we'll be left with hydrogen alone. But hydrogen will not tend to exist just on its own like that. Instead, it'll form hydrogen gas, which is H2. And when you do put this zinc metal in hydrochloric acid, you'll see a bubbling during the reaction, meaning that hydrogen gas is being given off. All right, so what we want to do now is put blanks out front of each item involved here, and we'll try to balance the equation. But there's one step we want to do first. We want to determine, is this the right formula for zinc coming together with chlorine? Now the thing about zinc is it may be capable of donating different numbers of electrons. So we'd want to look to the periodic table here. If we look in the periodic table of elements, the oxidation states are going to be in the upper right of each element. It looks like zinc actually can only donate 2 electrons. Some of these transition metals especially may form different oxidation states, like copper could give off 1 electron or 2 electrons, nickel could give off 2 electrons or 3 electrons. Zinc just has an oxidation state of 2, so let's assume that zinc is going to give off 2 electrons in this compound. If zinc gives off 2, it'll form a +2 ion, and chlorine always accepts 1. So we can cross those and show that our formula for zinc chloride is actually going to be ZnCl2. That's important to determine before you ever try to balance the chemical equation. You want to make sure that you have the right subscripts, the right number of elements in each compound. All right, now that we have that, we can go on to try and balance the equation. So let's see. I'm going to start with something that I know has to be done. We've got 2 hydrogens here on the right and only 1 hydrogen on the left. I also see that we've got 2 chlorines on the right and only 1 chlorine on the left, so it would make a lot of sense to put a 2 here. That'll take care of both of those problems. We now have 2 hydrogens and 2 chlorines on the left, and we have 2 chlorines and 2 hydrogens on the right. So hydrogen and chlorine are all satisfied now. We also see that there's 1 zinc on the right and just 1 zinc on the left, so that works out perfectly. Our balanced formula is going to be that there. We may see a double replacement reaction. Double replacement means that there's going to be 2 compounds where they're going to each switch partners. And nobody's going to be alone at the beginning, and nobody's alone at the end either. So let's go ahead and write a reaction for potassium iodide with lead 2 nitrate in a double replacement reaction. All right, so potassium iodide is going to have a K together with an I. Lead 2 nitrate will be PbNO3, but it is possible in both of these cases that there may be additional subscripts going on. And we'll figure that out in a minute. Over here, we need them to switch partners. So K is going to now come together with the nitrate, and lead will go together with the iodine. All right, let's determine the correct formulas for each of these compounds. All right, to do that, we want to find the oxidation states of each of these elements. Potassium forms an oxidation state of +1, so it always gives off 1 electron. It's in the first column, and that would be the case for all these elements. Iodine's on the other end of the table here. It will accept 1 electron generally, so they're a perfect match. 1K should balance perfectly with 1 iodine. So that is the correct formula. When it comes to lead nitrate, we want to know what does nitrate normally do when it bonds with things. So if we go down here to a table of polyatomic ions, we can see that nitrate normally forms a -1 ion, meaning it will accept 1 electron. Since it's lead 2 that they're talking about, the lead is going to be giving off 2 electrons each. So that makes this a +2, and this could be a -1. With that in mind, it's going to require 2 nitrates to satisfy 1 lead. So we want to put parentheses around the nitrate and say that there's going to be 2 of them. So what do I mean by that? I mean lead has 2 electrons to give. Each nitrate can accept only 1 electron, so it's going to require 2 nitrates to work together with a single lead. And that's why its formula will be lead nitrate with a 2 on the nitrate. Alright, so the potassium will give off 1 electron. Nitrate will accept 1, so they're actually balanced there. That is the final formula. Lead will give off 2 electrons, but iodine wants to accept just 1. Therefore, our chemical formula for lead iodide is going to be PbI2. Alright, let's put blanks out front now that we have the correct formulas for each of these. We'll try to balance the equation. So one thing that definitely has to happen is the potassium nitrate here needs to be doubled. I know that because we have 2 nitrates on the left and we only had 1 on the right, so this has got to be doubled. Now we have 2 nitrates on the right and 2 nitrates on the left. We could write that down if we want, just to help us analyze and organize the information. Let's see. We've got now 2 potassiums as a result of us putting a 2 out front. There's only 1 potassium over here, so the next thing that's absolutely required is we're going to have to double this guy. That's going to give us 2 potassiums on the left and 2 iodines on the left. It looks like that may balance it perfectly at that point, because our single lead here matches with the single lead there, and our 2 iodines on the left match with the 2 iodines on the right. Everything checks out, so that's going to be our balanced formula. Another type of reaction we might see is a combustion reaction. These are common with hydrocarbons, such as propane. When you burn a hydrocarbon, you're going to give off carbon dioxide and water as products, and energy, of course, as well. So let's look at an example of burning propane. We want to put the propane on the left. It'll combine with oxygen. You have to have oxygen to burn. And then we'll create carbon dioxide as a gas and water as a product. Now here all the chemical formulas are given, so we just want to balance the coefficients and then we're done. So we got 3 carbons on the left, only 1 carbon on the right. There's no question that we're going to have to triple this product here. So that's going to give us 3 carbons and 6 oxygens now. But we also see that we have 2 hydrogens and another oxygen, making a total of 7 on the right. We've got 8 hydrogens here and 2 oxygens there. I'm going to wait to balance the oxygen. Because it's alone, it can be fixed at the end no matter what. I can put any number out front I want in order to make that work out. So I'm going to focus on some of the other elements instead. So take, for example, Here we've got 2 hydrogens on the right, but 8 hydrogens on the left. There's no question that we're going to have to at least multiply this by a 4. Okay, so that'll now give us 8 hydrogens and 4 oxygens. So let's see who's balanced so far. Our carbons are balanced, our hydrogens are balanced, and the only one remaining is the oxygens. And that one, like I said, can be easily fixed. So how many oxygens do we have in all? That's a total of 10 oxygens on the right. Now our subscript is 2, so the best thing for us to multiply out front would actually be a 5. That would change our oxygens to 10. And now we have perfect balance. One of the other things we're going to want to do in these chemical equations is say what kind of state the chemicals are in. So certain ones just have known states, like oxygen gas, for example, is going to be a gas, so we put parentheses G to the right of it. Same thing with carbon dioxide. It's known to exist as a gas at room temperature. Okay, propane is also known to be delivered as a gas in a tank, so we'll call that a gas as well. H2O, as we know at room temperature, is a liquid, so we'll put L by that. Okay, quiz yourself by looking at these reactions and trying to determine what type are they. Are they synthesis reactions, where 2 components are coming together to form one? Are they decomposition reactions, where a single compound is breaking up into 2 parts? Are they single replacement, where one element or a polyatomic ion is switching partners? Are they double replacement reactions, where 2 compounds switch partners with each other? Or are they combustion reactions, where a hydrocarbon is being burned? Okay, this first one shows hydrogen gas combining with oxygen gas to make water. That is a synthesis reaction. Here we see that iodine switches partners. It was with the magnesium, and then later the iodine goes together with the silver. And the nitrate there switches from being with the silver to being with the magnesium at the end. That is a double replacement reaction. Here we see calcium carbonate breaking down into calcium oxide and carbon dioxide. This would be a decomposition because it's one compound breaking up into 2. And finally, we have octane combining with oxygen to make carbon dioxide and water. That is the burning of octane. It is a combustion reaction. Such as would be done in a gasoline engine.